two suns hang forever in a crimson sky. That famous scene from Star Wars is not just science fiction, it is a real cosmic possibility. Our galaxy is filled with binary star systems, pairs of stars locked in a gravitational dance, and orbiting them are some of the most incredible and bizarre planets we have ever discovered. By the end of this exploration, you will know 30 mind-blowing facts that completely reshape what a planet and a solar system can be. We will see worlds with triple sunrises, climates of pure chaos, and orbits defying all logic. How would life even begin on a planet that has no concept of a single, steady star? Our own familiar sky, with its single, steady sun, is the cosmic exception. The true galactic standard is not solitude but partnership. Astronomers now know that more than half of all the stars in the Milky Way are part of binary or even triple star systems. Our Sun, sailing alone with its family of planets, is actually somewhat of an outlier. This simple, profound shift in perspective changes everything. It means that planets orbiting two suns are not rare curiosities. They are likely one of the most common types of worlds in our galaxy. For every solar system like ours, there could be dozens where planets circle a pair of dancing stars. This fact fundamentally rewrites the textbook on where and how planets form. If binary systems are the galactic norm, then the strange and wonderful worlds we are about to explore are not the fringe of planetary science, they are at its very heart. But how can a planet even exist in such a chaotic gravitational environment? It all comes down to the precise geometry of the dance. Astronomers have identified three primary ways a planet can orbit a pair of stars, each creating a fundamentally different world. The first, and perhaps most stable, is called an S-type orbit. Here, the planet is a loyal companion to just one of the two stars, clinging to it in a tight embrace while the second star shines in the distance like a brilliant, permanent lantern. In this configuration, the planet's primary sun is close and warm, while its partner star orbits much farther out, a distant secondary light that might not even provide noticeable heat. It is a solar system within a solar system, a nested arrangement of celestial motion. The second type is the iconic one, the Tatooine orbit, formerly known as a P-type or circumbinary path. This is where the planet does not choose a side. Instead, it orbits both stars together, tracing a wide, grand circle around the entire binary pair. From the surface of such a world, you would see two suns rise and set together, or perhaps chase each other across the sky in a never-ending celestial waltz. This orbit requires a very specific balance. The planet must be far enough away from the stellar duo to avoid being violently pulled apart by their competing tugs of gravity. Then there is the third and most precarious path, the L-type orbit. This places a planet not around a star, but at a gravitational sweet spot called a Lagrange point. These are positions in space where the pulls from the two stars and the planet's own motion create a point of equilibrium, like a ball resting perfectly in the trough between two hills. A planet here would essentially orbit an empty point in space, with the two stars swinging around it in the sky. These orbits are extraordinarily delicate. A slight nudge from a passing asteroid or the gentle push of Starlight could destabilize the entire arrangement, sending the world spiraling away into the void. The idea of a stable planet circling two suns remained a theoretical dream until the autumn of 2011. That year, data from NASA, a Kepler space telescope, delivered an announcement that sent shockwaves through astronomy: the confirmed discovery of Kepler 16b. This was not a speculative model or a hopeful signal. It was a real world, a genuine Tatooine orbiting a pair of stars roughly 200 light-years away. Its existence was a monumental proof of concept, demonstrating that the delicate gravitational ballet of a circumbinary orbit could indeed result in a stable, long-lasting planet. Kepler 16b shattered the assumption that binary star systems were planetary dead zones, instantly opening an entirely new frontier in the search for worlds beyond our solar system. This pioneering planet is a cold, gaseous giant, comparable in size to our own Saturn. It completes one full orbit around its twin suns in about 229 Earth days, tracing a path that happens to fall within the system's broad habitable zone, the region where temperatures could allow for liquid water. But do not picture a life-bearing world. Kepler 16b is a gas giant with no solid surface, a frozen realm where any hypothetical moon would be bathed in the gentle, perpetual light of two setting suns. Its profound significance lies not in its hospitality, but in its mere existence, by confirming that planets could form and persist in such a complex environment. Kepler 16b transformed circumbinary planets from science fiction into a vibrant, new branch of astronomical reality, inviting us to wonder what other impossible-seeming worlds might be waiting in the double light of distant suns. For a visitor standing on a world like Kepler 16b, the sky would deliver a daily masterpiece of celestial motion. The two stars, locked in their own intimate dance, would orbit around a common center of gravity, and this motion paints the heavens with an impossible brush. Their orbital period might be just a few days or even less than one Earth day, meaning their positions relative to each other and to the horizon would change from sunrise to sunrise. You would not simply have a day and a night, you would have a symphony of light. Some days, both suns might rise together in a blaze of coordinated glory, casting twin, sharply defined shadows that slowly merge as the stars climb. On other days, one star could crest the horizon first, painting the sky in deep oranges and reds, only to be joined an hour later by its brilliant companion, dramatically shifting the color and intensity of the light. The sunsets would be even more spectacular, a layered event where one star might dip below the horizon while the other lingers, creating a prolonged twilight of shifting hues. There could be days where the stars eclipse each other from the planet's perspective, causing a sudden, deep dimming in the middle of the day, a stellar wink before the full light returns. This is not a static postcard, it is a dynamic, living painting. The very length of daylight, the heat you feel on your skin, and the color of the sky would be in constant, gentle flux, dictated by the ever-changing geometry of those two orbiting suns. It makes our single, predictable sunrise seem almost mundane by comparison, a quiet solo performance in a universe that often prefers a dazzling, chaotic duet. This constant celestial dance introduces a profound challenge for any world hoping to host life. The very idea of a habitable zone becomes wonderfully chaotic. In our solar system, the habitable zone is a relatively stable, donut-shaped region around our single sun, where temperatures are just right for liquid water to exist on a planet's surface. But around two stars, this comfortable ring shatters into a far more complex shape. You have not one, but two sources of heat and light, each moving in relation to the other and to the planet itself. The result is not a zone, but a dynamic, pulsating field of possibility. Astronomers model it as a region that breathes, expanding and contracting as the stars swing closer together or farther apart in their own orbit. A planet on a circumbinary path does not sit in one steady spot within this zone. It journeys through its evolving contours. For part of its long year, the planet might bask in the combined warmth of both suns at their closest approach, pushing it into a temporary greenhouse state. Then, months later, as those stars drift to the farthest points in their dance, the planet might receive only their isolated, diminished light, plunging it into a deep chill. This means a world could be cyclically pushed in and out of theoretically habitable conditions, experiencing climatic seasons that last for decades or centuries, all dictated by the grand orbital clockwork of its twin suns. Finding a planet in such a system that maintains a stable, life-friendly climate becomes a breathtaking puzzle, requiring a perfect synchronization between the planet's orbit and the star's own rhythmic motion. This gravitational tug-of-war does far more than just paint pretty sunsets. It physically sculpts the paths these worlds can take. In a stable system like our own, a planet's orbit is a nearly perfect circle, a gentle ellipse maintained by the steady pull of a single sun. But place that same planet between two competing gravitational masters, and its path becomes a stretched and stressed oval, a state astronomers call a highly eccentric orbit. The planet is caught in a relentless cosmic pull, yanked one way by the closer star, then whipped back as the other star gains influence during its own orbital swing. This constant gravitational massage has a profound physical effect on the world itself, a process known as tidal heating. As the planet's orbit is stretched and squeezed by the twin stars, its very interior flexes. Rock grinds against rock, layers of mantle and core slide with friction, and this immense internal energy transforms into heat. Think of it like repeatedly bending a metal coat hanger. After a few dozen bends, the point of stress becomes too hot to touch. Now imagine that happening to an entire planet, continuously, for billions of years. This means a distant, icy moon or a cold gas giant world, far outside the traditional habitable zone and receiving little warmth from its suns, could have a molten, volcanic core churned to life solely by this gravitational kneading. A frozen crust could hide a global subsurface ocean kept liquid by this internal furnace, or its surface could be cracked by spewing volcanoes erupting slush and ammonia instead of lava. Tidal heating rewrites the rules of where geological activity, and perhaps even the ingredients for life, can exist, turning frigid wastelands into worlds of hidden, gravitational fire. This relentless gravitational push and pull means the line between a stable orbit and cosmic catastrophe is razor thin. For a planet circling two suns, getting too close to the center of that stellar dance is a death sentence. The region around the binary stars is a gravitational maelstrom, a zone of such intense and competing tugs that no stable, circular orbit can hold. If a planet ventures into this chaotic inner space, its fate is almost always violent ejection. One particularly strong gravitational kick from a close pass by the primary star, amplified by the secondary star's pull, can act like a cosmic slingshot, hurling the planet out of the system entirely at tremendous speed. It becomes a rogue world, condemned to drift forever in the frigid darkness between stars, its twin suns shrinking to mere points of light before vanishing entirely. The alternative fate is just as grim, a decaying spiral inward, drawn into a fatal embrace with one of the stars in a fiery collision. This ever-present threat of destabilization is why the discovery of Kepler-16b was so revolutionary. It proved that a stable, long-term parking orbit, far enough from the stellar chaos to be safe, was not just a theory. That planet's existence showed us a path through the gravitational minefield, a precise orbital distance where the combined pull of the two stars creates a harmonious, predictable path rather than a chaotic one. Most planets that form in these turbulent nurseries likely do not find that safe harbor, which makes the survivors we can detect, those rare worlds in the calm beyond the storm, all the more precious and fascinating. The violent ejection of a world is not the only path through this gravitational labyrinth. Another is a slow, inward spiral. Planetary migration is a process where a young planet, after its formation, does not stay put. Gravitational tugs from the surrounding gas and dust of its birth disk, or powerful interactions with other newborn planets, can cause it to gradually drift closer to its star. In the serene environment of a single star system, this already creates bizarre worlds like hot Jupiters, gas giants that bake terrifyingly close to their suns. But in a binary system, this migration becomes an epic odyssey. The planet must now navigate the shifting gravity wells of two stars, not one. Its journey inward is no longer a simple drift toward a single point of light. It is a perilous slalom between two massive, moving anchors. This complex dance can steer a planet into orbits that would be impossible around a solitary star, perhaps locking it into a resonant pattern where its orbital period is a precise fraction of the star's own orbital period. The migration might even be accelerated, the combined gravitational pulls acting like a brake or a slingshot, hurling the world into a scorchingly close embrace with one of the suns far faster than would normally occur. This means the hot Jupiters we find in binary systems may have endured a far more turbulent and dramatic history than their cousins in single-star systems, survivors of a celestial obstacle course that most planets would not have endured. Yet the greatest threat to a planet's existence may come long before it even forms. The serene, dusty nurseries where worlds are born face a brutal challenge in a binary system. Around a young star, a vast, flat disk of gas and dust slowly coalesces, its particles gently sticking together over millions of years to build the seeds of future planets. This protoplanetary disk requires peace and quiet, a stable, rotating platform for gravity to do its delicate work. Now introduce a second star. As this companion swings through its orbit, its gravity acts like a cosmic plow, carving through the disk. It shears the outer edges, truncating the disk to a much smaller size than it would otherwise be, and in extreme cases, it can rip the entire structure apart, scattering the precious planetary building blocks into the void. For a close binary pair, this means the raw material for planets is severely limited or stolen away before the construction can even properly begin. This is why, for decades, astronomers assumed close binary stars were planetary deserts. The very violence of their dance seemed to forbid the gentle art of world building. The fact that we find planets there at all, like Kepler 16b, is a staggering revelation. It means planet formation is not a fragile process easily snuffed out, but an incredibly resilient and stubborn force of nature. Some disks must be dense and massive enough to withstand the stellar onslaught, or the planetary seeds must form with astonishing speed, consolidating into robust, gravitationally bound bodies before the second star's next disruptive pass. Each world we discover in a tight binary is therefore a cosmic survivor, a testament to formation processes that refused to be silenced by the chaos. This gravitational interference can operate on timescales so vast they defy imagination, through a subtle but relentless process known as the Kozai-Lidov mechanism. Think of it as a cosmic whisper, a gravitational conversation between a planet and the distant second star that slowly, over hundreds of thousands of years, rewrites the rules of an orbit. Here is how it works in simple terms. A planet orbiting one star in a binary pair is not just tugged by its host, it also feels a persistent, gentle pull from the faraway companion star. This distant influence does not immediately yank the planet away. Instead, it acts like a metronome, a steady rhythm that resonates with the planet's own motion. Over immense stretches of time, this resonance transfers energy, but in a very specific way. It trades one orbital property for another. The mechanism slowly drains circularity from the planet's path, making it more stretched and oval, what we call increasing its eccentricity. In exchange, it pumps up the planet's tilt, its orbital inclination. A world that began its life in a flat, calm, circular orbit around its sun can be gradually transformed. Its path becomes a wild, steeply tilted ellipse. For much of its long year, such a planet would be a frozen outcast in the distant reaches of its system. Then, in a brief, scorching close pass near its star, it would swing in for a searing blast of heat before being flung back out into the deep freeze. This cyclical transformation from icebox to furnace and back again would make any notion of a stable, life-friendly climate almost impossible. The Kozylidov mechanism reveals that even in seemingly stable S-type orbits, where a planet faithfully circles one star, the silent partner in the distance holds a long-term power to utterly reshape a world's destiny. The gravitational stresses of a binary system can forge a world of pure, unyielding extremes. Consider a planet that has migrated perilously close to one of its twin suns, falling into a gravitational embrace so tight it becomes tidally locked. Just as our moon always shows the same face to Earth, this world would forever turn one hemisphere toward its stellar host, and the other toward the cold void of space. The result is a planet divided, a permanent border between blazing light and endless shadow. On the day side, the conditions are beyond anything in our solar system. Not only does this hemisphere face the relentless glare of its primary sun, but periodically, the second star swings into view as well. For parts of the binary orbit, this world would be roasted by a double sunrise, a combined stellar fury that could push surface temperatures to thousands of degrees, enough to melt rock and metal into glowing, global seas of lava. The atmosphere, if one could exist, would be perpetually superheated into a howling, supersonic gale racing from the day side to the night. And then there is the night side, a hemisphere that has never seen a sunrise. Shielded eternally from any direct starlight, it plunges into the deepest cold imaginable, a frozen, airless wasteland where any atmosphere would condense and fall as snow, leaving a vacuum as profound as open space. The border between these two realms, the Terminator line, would be a place of surreal drama, a perpetual twilight zone where the searing heat of day battles the absolute cold of night. Here, in a narrow, tortured band, temperatures might be moderate enough for exotic geological processes, perhaps even for volatile compounds to briefly exist in liquid form before boiling away or freezing solid. This is not a world of seasons or cycles. It is a monument to gravitational imprisonment, a stark reminder of how binary stars can sculpt not just orbits, but the very face of a planet into realms of absolute light and utter darkness. The stability of light and heat is a luxury our solar system takes for granted. For a planet orbiting two stars, the radiation environment is a chaotic battlefield. Each sun in a binary pair can dramatically influence the other, turning what should be a steady stream of energy into a volatile, unpredictable storm. One star might be a quiet, stable furnace like our sun, while its companion is a tempestuous red dwarf, prone to erupting with monstrous stellar flares. These flares are not mere bursts of light. They are cataclysmic explosions of high-energy radiation and charged particles that blast out into space. In a binary system, a planet can find itself caught in the crossfire, subjected to a double dose of such violence. Even if both stars are relatively calm, their gravitational dance can trigger activity. As they swing close together, their magnetic fields can tangle and reconnect, sparking immense flares far more powerful than anything either star would produce alone. For a nearby world, this means the cosmic weather forecast is one of permanent uncertainty. A calm, sunny morning could, without warning, transform into a lethal radiation event, bathing the entire planet in a surge of X-rays and ultraviolet light powerful enough to scour its surface and shred the chemical bonds of any nascent life. But the danger is not only from sudden explosions. In some intimate binary pairs, the stars are so close that one can literally feed off the other. This is called mass transfer, where the stronger gravity of one star pulls a stream of gas directly from the atmosphere of its companion. This stolen material spirals in, superheating to millions of degrees and glowing with intense, high-energy radiation before it crashes onto the surface of the devouring star. Any planet in this system would be bathed in a permanent, searing bath of this accretion radiation, a relentless torrent far more energetic than normal starlight. It is a scenario where the sky itself becomes a source of deadly poison, capable of ionizing and stripping away a planet's atmosphere molecule by molecule over millions of years. Even if a world miraculously held onto its air, the surface would be sterilized, its chemistry broken down by the constant barrage. This variable and often extreme radiation environment presents one of the greatest challenges to life in binary systems. It demands not just a stable orbit in a warm zone, but a planetary fortress, a world with a powerful magnetic field and a thick, protective atmosphere to act as a shield against a sun that can, without warning, become a weapon. Finding these cosmic survivors required a new kind of astronomer's eye, one that could patiently watch for the faintest flicker of distant light. NASA's Kepler Space Telescope was that eye, and its design was revolutionary. Instead of scanning the whole sky, Kepler was pointed at a single, dense starfield in the constellations Cygnus and Lyra, and it stared, unblinking, for 4 years. This unwavering gaze made it the perfect hunter for worlds in binary systems. The key was the transit method, watching for the tiny, periodic dip in a star's brightness caused by a planet crossing in front of it. In a binary system, this signal becomes a fantastically complex puzzle. Not only do you have to spot the planet's transit, but you must first untangle the overlapping light of 2 stars and then account for their own eclipses as they orbit each other. Kepler's sensitive instruments and its marathon observation campaign allowed scientists to do just that, to pick out the precise, repeating rhythm of a planet's shadow from within the chaotic symphony of a double star's dance. It was this relentless, patient stare that unveiled Kepler 16b and proved that Tatooines were real. Now, the search has expanded to the entire celestial sphere with Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS. While Kepler gave us a profound, deep look at one cosmic neighborhood, TESS is conducting a grand census of the whole sky. It scans vast sectors, month by month, searching for planets transiting the brightest stars near our solar system. This broader net is already catching more of these exotic binary systems, and with a crucial advantage, because TESS focuses on brighter, closer stars, the planets it finds are far better targets for the next step, atmospheric investigation. This is where the vision becomes truly breathtaking. Once TESS identifies a circumbinary world, the incredible power of the James Webb Space Telescope can be brought to bear. As that planet transits, a sliver of its host star's light filters through its atmosphere. Webb can analyze that filtered starlight, breaking it into a spectrum that reveals chemical fingerprints, the telltale signs of water vapor, methane, or even potential biosignatures like oxygen. We are on the verge of not just finding these double-sun worlds, but of sniffing their air, of asking for the first time what the sky might smell like on a planet with two setting suns. The universe, it seems, is always ready to outdo our wildest imaginations. While two suns are astonishing, some worlds are born into a family of three. In the constellation of Centaurus, a staggering 250 light-years away, lies the system HD 131399 and its planet, HD 131399ab. Discovered in 2016, this world shattered our preconceptions of what a solar system could be. It is a gas giant, several times more massive than our Jupiter, but its true claim to fame is its address. It lives in a triple star system. The arrangement is a celestial hierarchy of breathtaking complexity. The planet itself orbits the largest and brightest of the three stars, a star we will call Star A. In an orbit so vast, it takes the planet 550 Earth years to complete a single year. That primary star, Star A, is itself the center of a wider dance. Orbiting it at a much greater distance is a close-knit binary pair, stars B and C, which whirl around each other every few days. Together, this dancing duo of stars orbits the primary, Star A, in a grand, slow waltz. From the perspective of the planet, this creates a sky of impossible beauty. For the majority of its long year, the planet would see its primary sun, Star A, as a brilliant disk in the sky. The distant binary pair, stars B and C, would appear together as a single, intensely bright point of light, like a supercharged permanent star. But then, for a period of about 140 Earth years, as the planet moves through a specific part of its orbit, the geometry aligns perfectly. All three stars would be visible in the daytime sky. The primary would dominate, while the binary pair, still close together, would rise and set at a different time. This means the planet would experience genuine triple sunrises and triple sunsets, a daily light show lasting for generations of any potential inhabitants. The very existence of this planet is a profound mystery to astronomers. How could a giant planet form and survive in such a dynamically tense environment? The competing gravitational pulls from three stars should, in theory, have ripped apart the protoplanetary disk or destabilized any fledgling world. One leading theory suggests it may have formed much closer to its primary star and then been violently flung outward into this wide, uneasy orbit by a gravitational encounter with another massive object. Another possibility is that it formed in a much more placid region and was later captured by this triple star family. HD 131399ab stands as a monument to cosmic chaos, a world that by all rights should not be there, painting its triple-hued light across the void. Our cosmic treasure hunt takes a turn toward the truly extravagant with the possibility of diamond worlds. We have already seen how binary systems can forge worlds of fire and ice, but they might also be the universe's ultimate jewelers. This idea starts with a specific type of binary pair where one star has already died, collapsing into a dense, Earth-sized ember called a white dwarf. These stellar remnants are often incredibly carbon-rich, the ashes of nuclear fusion. In a close binary dance, the gravitational tides between the white dwarf and its living companion can become a cosmic conveyor belt. Material, particularly carbon, can be stripped from the white dwarf's outer layers and funneled onto any nearby planet orbiting the other star. Imagine a world subjected to a continuous, gentle rain of pure carbon dust for billions of years. As this carbon accumulates on the planet, perhaps a rocky world several times Earth's mass, it gets buried under newer layers. The pressure in the planet's mantle builds to staggering levels, millions of times greater than Earth's atmospheric pressure. Under these extreme conditions, the carbon atoms are forced into a rigid, crystalline structure, the very same structure that forms deep within Earth to create diamonds. The result would not be a planet glittering with surface gems, but something far more profound, a world with a mantle not of silicate rock-like Earth, but of solid diamond. This diamond layer could be hundreds of miles thick, a geological stratum of unimaginable wealth and strangeness. The planet's tectonic processes, its volcanic activity, even the very way it cools, would be governed by the unique properties of carbon and diamond. While no such world has been definitively found, the physics is sound. In the turbulent, material-exchanging environment of certain binary star systems, the universe might be quietly crafting the most opulent planets imaginable, worlds with hearts of celestial crystal. Some of the most stunning cosmic vistas are sculpted not by planets, but by the unseen hand of a second star. Consider the Fomalhaut system, a brilliant star just 25 light-years away, famous for its dazzling ring of icy debris. For years, astronomers have watched a single speck of light, dubbed Fomalhaut b, move along the inner edge of this ring, a potential planet caught in the act of clearing its orbit. The nature of that speck is hotly debated. It might be a true world or just a temporary clump of colliding dust, but the real story of this system lies in its hidden architecture. Fomalhaut is not one star, but three, a trinary system, and its smallest, dimmest member, a red dwarf named Fomalhaut c, holds a gravitational paintbrush. This tiny, distant star orbits so far out that it takes millions of years to complete a single loop, yet its gentle, persistent tug is the master artist behind the scene. It is Fomalhaut c's gravity that shepherds and squeezes the vast debris belt around the primary star, pulling it into a strikingly narrow, elliptical shape. From our vantage point, this creates an iconic image, a brilliant central star surrounded by a sharp, tilted ring of glowing dust, an appearance that has earned it the nickname the Eye of Sauron. This is not just a pretty picture, it is a profound lesson. It shows us that a companion star, even a faint and distant one, can be the dominant architect of an entire planetary system's structure. It molds the construction zone, dictating where dust can collect and where planets might one day form, proving that in binary systems, the landscape of creation is always a collaborative work of art. But the most extreme survivors in the cosmos circle not living suns, but the dead. The first planets ever discovered beyond our solar system were not found in a gentle, sun-drenched system like ours. In 1992, astronomers made a historic detection, and the location was as shocking as the discovery itself. These pioneering worlds orbit a pulsar, a rapidly spinning neutron star, the dense, city-sized corpse left behind after a supernova explosion. This pulsar, known as PSRB 1257+12, is itself part of a binary system, with a companion white dwarf star. The environment here is a realm of pure extremity. The pulsar emits a lighthouse-like beam of intense radiation that sweeps through space with every rotation, and its gravitational field is so powerful it warps the fabric of spacetime itself. For a planet to exist here is to endure a perpetual storm of X-rays and gamma rays, bathed in the ghostly glow of a stellar grave. These are not first-generation worlds, born in a calm disk of dust. They are almost certainly second-generation, phoenixes risen from apocalyptic ashes. The leading theory is that the supernova that created the pulsar did not completely destroy its original planetary system. Instead, the explosion's debris, a cloud of heavy elements, fell back into orbit. From this radioactive wreckage, new planets coalesced, forged in fire and fury. They are worlds built from the bones of a dead star, orbiting a cinder that ticks with the precision of an atomic clock. Their very existence proves that planet formation is a stubborn, universal process, capable of occurring in the most hostile environments imaginable, even in the blinding glare of a cosmic tomb. The resilience of these worlds is not a solitary fluke, for some binary systems have managed to build entire families. For decades, the chaotic gravitational environment of two stars was thought to be a planetary limit, capable of supporting perhaps one hardy survivor at most. The discovery of the Kepler-47 system shattered that assumption completely. Here, nearly 5,000 light-years away in the constellation Cygnus, two stars, one sun-like and one a dim red dwarf, orbit each other every 7.5 days. And around them, both tracing wide, stable circles in the void, are not one, but at least 3 confirmed planets. This is the first known circumbinary system with multiple worlds, a miniature solar system with 2 suns at its heart. The architecture is a marvel of gravitational engineering. The innermost planet, Kepler-47b, is a sweltering world about 3 times the size of Earth, whipping around its twin suns in just 49 days. Farther out, in the system's broad habitable zone, orbits Kepler-47c, a gas giant roughly the size of Neptune. This world is a tantalizing thought experiment, for while it has no solid surface itself, any large moon in its orbit would be bathed in gentle, double sunlight at a potentially life-friendly temperature. The outermost known member, Kepler-47d, is another gaseous world, larger still, completing its stately orbit in just over 300 Earth days. Their stable coexistence is the true revelation. It proves that the gravitational whirlwind of a binary pair can be negotiated not just by a single planet, but by a whole chorus of them, each finding its own harmonious path within the complex music of the stars. This expands the canvas for life and complexity exponentially, suggesting that binary systems are not planetary deserts, but can be fertile grounds for building intricate, multi-world systems as rich and diverse as our own. Yet even within these intricate families, a world can be born traveling the wrong way. In the serene order of our solar system, every planet orbits the Sun in the same direction, a prograde motion that matches the Sun's own spin, a legacy of the swirling disk from which they all formed. But in the gravitational playground of a binary system, this cosmic traffic rule is sometimes spectacularly broken. Astronomers have discovered planets in retrograde orbits, worlds that move backward, orbiting their star in the opposite direction to the star's rotation, or even contrary to the binary pair's own dance. Imagine a planet that rises in the west and sets in the east, its path a defiant reversal of the celestial flow. This is not a minor quirk. It is a fundamental rebellion against the natural order of planetary birth. A planet cannot form this way from a standard disk. The physics forbids it. So how does a world end up on such a backward path? The answer lies in the profound gravitational influence of the second star. In a close binary system, the companion star's gravity acts as a persistent, destabilizing force. It can deliver a series of gentle but precise gravitational nudges to a planet over millions of years, slowly tilting and warping its orbit. In extreme cases, these nudges can build up to a single, catastrophic gravitational kick, a cosmic slap that flips the planet's orbit entirely, turning it 180 degrees. It is as if the planet were a spinning top given a sharp flick, sent careening in a new, inverted direction. Alternatively, a dramatic close encounter with another massive planet in the system could achieve the same violent result, a gravitational slingshot maneuver that sends the victim into a backward loop. These retrograde worlds are living records of past chaos, their backward motion a permanent scar from a long-ago gravitational battle. They prove that in binary systems, a planet's final orbit is not always its birth orbit, but can be the result of a dramatic, late-stage rearrangement, a celestial U-turn written in the laws of motion. This detective work is complicated by cosmic illusions. One of the greatest challenges in hunting for planets around two suns is the sheer number of imposters. The complex geometry of a binary system is a master of deception, capable of producing signals that look, for all intents and purposes, exactly like a transiting planet. When two stars orbit each other, they regularly eclipse one another from our perspective, creating deep, predictable dips in their combined light. But what if the eclipse is not perfectly clean? A vast, diffuse cloud of dust or debris swirling around one of the stars can drift into the line of sight. As this cloud passes in front of the stellar disk, it subtly dims the light, not with the sharp, clean cut of a solid planet, but with a fuzzy, gradual fade. From thousands of light years away, with our instruments straining to catch the faintest flicker, that fuzzy dip can be incredibly difficult to distinguish from the real thing. Even more convincing are scenarios where the stars themselves are not perfectly spherical. Some stars, especially in close binary pairs, are stretched into egg shapes by their mutual gravity. As these distorted stars rotate, the amount of surface area pointing toward us changes, causing their brightness to vary in a regular pattern. That rhythmic brightening and dimming can perfectly mimic the clockwork signal of an orbiting planet. For every true discovery like Kepler 16b, astronomers must rule out dozens of these clever mimics. They do this by building incredibly detailed computer models of the binary stars themselves, accounting for their shapes, their temperatures, their exact orbital dance. They then see if the observed light dips can be explained purely by stellar physics and geometry. If the model fits without a planet, the signal is likely an illusion. But if a tiny, repeating dip remains unexplained after all stellar effects are accounted for, that persistent anomaly becomes the heartbeat of a hidden world, a true planet revealing itself from within the stellar noise. It is a meticulous process of elimination, separating the celestial reality from a universe of compelling shadows. Separating that planetary heartbeat from the stellar noise is a monumental task, one that has opened the door to a new kind of astronomer. Beyond the powerful computers and complex algorithms, some of the most sensitive detectors in this search are human eyes. This is where the Project Planet Hunters TSS transforms anyone with an internet connection into a cosmic explorer. The mission's telescope generates a flood of light curve data, graphs that plot a star's brightness over time. For a single star, software can efficiently flag the clean, periodic dips of a potential planet. But for binary stars, the data is a tangled web, a mess of overlapping eclipses and subtle variations. Here, the pattern recognition prowess of the human brain becomes an invaluable tool. Volunteers on the Planet Hunters website are presented with these complex light curves and asked a simple question: does this look like it could have a planet's trance hidden within the stellar dance? The human eye is exceptionally good at spotting the slight asymmetry of a real transit, the specific shape of a dip that a star's natural flickering or an algorithmic glitch would not produce. It is a global effort in collective attention, where a retired teacher, a night shift worker, or a curious student can scan the same data as a professional astrophysicist. And this collaboration has borne incredible fruit. Citizen scientists have been instrumental in identifying dozens of promising candidate circumbinary planets within the TESS data, targets that might have been overlooked by automated systems. Each flagged candidate is a potential new world, a Tatooine waiting for professional confirmation. This process beautifully democratizes discovery, proving that in the age of giant telescopes, the curious human mind remains one of our most essential instruments for mapping the double-sunned frontiers of our galaxy. The line between a star and a planet is not as sharp as our textbooks might suggest. Between the brilliant furnaces of true stars and the cold, dark worlds we call planets lies a mysterious middle ground, the realm of the brown dwarf. These are cosmic underachievers, objects too massive to be called planets, yet too small to ignite the sustained hydrogen fusion that defines a true star. They are failed stars, glowing faintly with the residual heat of their formation and the slow smolder of deuterium fusion, destined to cool and fade over billions of years. And just like true stars, brown dwarfs often come in pairs, forming binary systems of their own. These are not systems of light, but of lingering warmth, where two dim orbs circle each other in a perpetual twilight. The discovery of planets around such pairs pushes our definitions to the breaking point. We call them planetary mass companions, but what are they truly orbiting? A pair of failed stars. This creates a bizarre celestial hierarchy that blurs every category we have. Is it a binary star system with planets, or is it a planetary system with two incredibly large, failed central bodies? The answer is both and neither. These systems represent a fascinating middle ground in cosmic formation, proving that nature does not care for our neat classifications. In these dim binaries, the process of building worlds operates in a strange, scaled-down environment, where the architects are themselves ambiguous objects, neither fully star nor planet, quietly hosting their own families in the gloom. But to truly know these worlds, we must move beyond their shadows and see their light. The transit method has been our faithful guide, revealing planets by the subtle dimming they cause as they pass in front of their stars. Yet it gives us only measurements: mass, radius, orbit. It tells us nothing of a world's face, its colors, or the chemistry of its sky. The next great leap requires us to see the planet itself, to capture its faint glow separate from the blinding glare of its suns. This is the frontier where the James Webb Space Telescope begins its revolutionary work. Direct imaging of an exoplanet is one of the hardest challenges in astronomy, akin to photographing a firefly hovering next to a distant searchlight. For planets in tight binary orbits, the task is nearly impossible, their light hopelessly lost in the combined glare of two close stars. But for worlds in wider binary systems, where a planet orbits one star at a great distance while its companion star shines far away, Webb's capabilities change the game. Its giant mirror and sophisticated coronagraphs, instruments designed to block starlight, can suppress the glare of that single host star, potentially allowing the faint infrared glow of a large, young, still warm planet to emerge from the darkness. We could, for the first time, get a direct pixelated image of a world in a double star system, measuring its temperature and perhaps even glimpsing hints of cloud patterns in its atmosphere. Yet Webb's most transformative power may lie not in imaging, but in sniffing the air of worlds we already know are there. For transiting planets in binary systems, especially those found by TESS orbiting bright, nearby stars, Webb performs a kind of celestial chemistry. As the planet crosses in front of its host star, a tiny fraction of that star's light filters through the planet's atmosphere. Molecules in that atmosphere absorb specific colors of light, leaving dark lines in the star's spectrum like a barcode. Webb's exquisite infrared sensitivity is built to read that barcode. It can detect the fingerprints of water vapor, methane, carbon dioxide, and even potential biosignatures like oxygen or combinations of gases that suggest biological activity. Doing this for a planet orbiting one star in a binary pair is complex enough, but Webb's instruments and the brilliant minds operating them are developing methods to untangle the overlapping light. They can model the precise contribution of each star in the system at the moment of transit, isolating the signal that comes only from the thin ribbon of atmosphere backlit by its primary sun. Imagine the moment when the data streams in from a world like Kepler 16b's hypothetical moon, or a new Earth-sized planet in a binary habitable zone. The analysis could reveal not just a list of gases, but a portrait of a climate, a carbon cycle, perhaps even the faint, tantalizing signature of something that should not exist without a helping hand. This is the ultimate promise, to move from knowing these double-sunned worlds are there, to beginning to understand what it might be like to breathe beneath their skies. The climate of a circumbinary world is not a steady state, but a grand symphony conducted by the orbital dance of its twin suns. On Earth, our seasons are a gentle rhythm, a predictable tilt toward and away from a single, constant source of light and heat. But for a planet orbiting both stars, that rhythm shatters into a complex, multi-layered composition of extremes. The key variable is not a planet's axial tilt, but the ever-changing distance between the two stars themselves. As these suns swing through their own intimate orbit, their combined output of energy reaching the planet fluctuates dramatically. When the stars are at their closest, huddled together in their dance, the planet experiences a double summer. It is bathed in the combined, focused warmth of both suns, a surge of stellar energy that could bake its surface and evaporate entire shallow seas. The atmosphere would churn with the intensity of this heat, driving hurricanes of unimaginable power and scale. Then, as the stars drift to the farthest points in their orbital embrace, their light becomes isolated and diminished. The planet plunges into a profound, double winter. The feeble, separated glow from each distant sun provides little warmth, potentially triggering a global deep freeze where the atmosphere itself could begin to snow out, collapsing onto the surface in vast glaciers of frozen nitrogen or carbon dioxide. This creates seasonal cycles not of months, but of decades or even centuries, a climatic pendulum swinging between inferno and ice age. The weather patterns emerging from such radical shifts would be beyond chaotic. Imagine superstorms that form as the planet lurches from a hot phase into a cooling one, where the temperature differential between the equator and the poles becomes so severe it whips the atmosphere into a permanent frenzy. Rainfall could be a rare, catastrophic event, followed by centuries of hyper-arid drought. For any form of life, this is not a challenge of adaptation, but of survival against a sky that constantly rewrites the rules of physics. A world might be technically within the habitable zone on average, yet spend 90% of its long year as either a scalding desert or a frozen snowball, leaving only a narrow window of climatic grace where liquid water could briefly flow. This turns the search for life in these systems into a hunt for a planetary tightrope walker, a world with just the right atmospheric composition and ocean coverage to buffer these wild swings, maintaining a tenuous equilibrium in the face of a celestial light that can never make up its mind. The violence of a young binary system may have a dark and prolific legacy, a factory line of cosmic orphans. Among the most haunting objects in the galaxy are rogue planets, worlds untethered from any star, drifting alone through the eternal night of interstellar space. For years, their origin was a profound mystery. How could a planet form without a star to cradle its birth? The answer may lie in the very chaos of binary star systems. Astronomers have developed a dramatic hypothesis, the rogue planet factory model, which suggests these lonely worlds are not born in isolation, but are violently exiled from their stellar homes. In the crowded, gravitational frenzy of a young binary system, the process of planet formation is a high-stakes game of pinball. Dozens of protoplanets, the rocky and icy seeds of future worlds, jostle for space within the turbulent disk. The two central stars exert a constant, destabilizing pull, their gravity acting like unpredictable bumpers on a cosmic table. In this environment, a gentle nudge can become a catastrophe. A close gravitational encounter between two protoplanets, amplified by the tug of a passing star, can impart a tremendous burst of speed. This slingshot effect can easily exceed the system's escape velocity, the speed needed to break free of its gravitational hold entirely. The result is not a single, rare ejection, but a potential exodus. A young, dense binary system could efficiently fling out countless protoplanetary bodies before they ever had a chance to mature into full-fledged planets. These embryonic worlds, some perhaps as large as Earth or even Neptune, would be cast adrift while still hot from their formation, glowing faintly in the infrared as they begin an endless journey into the void. This theory transforms our understanding of rogue planets. It means a significant portion of the galaxy's solitary wanderers may not be orphans from single-star systems, but refugees from a double-starred war zone, their existence a silent testament to the gravitational fury of their youth. The ultimate fate of a solar system is written in fire. For a planet orbiting one star in a binary pair, its destiny is tied to the life cycle of its stellar parent. Every sun-like star, including our own, will one day exhaust the hydrogen fuel in its core. In its death throes, it will swell into a monstrous red giant, a ballooning sphere of plasma that can easily engulf the inner worlds of its system. In a binary system, this stellar metamorphosis is a cataclysm that reshapes everything. The inner planets, those loyal companions that once basked in gentle sunlight, are vaporized, their atoms scattered and absorbed into the stars' expanding outer layers. But for the outer worlds, the story is different. A gas giant or an icy body orbiting far from the chaos might just survive. As the dying star puffs off its outer layers in a beautiful, expanding planetary nebula, it leaves behind its incredibly dense, Earth-sized core, a white dwarf. This stellar cinder, glowing with residual heat, becomes the new gravitational anchor, and around it, in a now vastly expanded orbit due to the mass lost during the red giant phase, the survivor planets remain, silently circling the grave of their former sun. The companion star in the binary pair watches this entire apocalyptic transformation from a distance, its own light now the dominant source in a system forever altered. Astronomers believe we are now beginning to detect the grim evidence of this process. Around some white dwarfs in binary systems, telescopes have spotted the chemical signatures of heavy elements like iron, nickel, and silicon, polluting the dwarf's pristine hydrogen or helium atmosphere. A white dwarf's gravity is so intense that any light elements should sink rapidly out of sight, leaving a pure atmosphere behind. The presence of these rocky metals can only mean one thing: recent accretion. Something rich in those elements is falling onto the white dwarf, the leading suspect, the shattered remains of a planet that survived the red giant phase, but not the gravitational turmoil that followed. Perhaps a survivor world, its orbit destabilized by the complex gravitational changes, was torn apart by the white dwarf's tides, creating a dusty ring of debris that now slowly rains down upon the dead star. We may be witnessing the final dissolution of a planetary core, the last remnants of a world that outlived its sun only to be consumed by its corpse. This offers a sobering, prophetic glimpse into the distant future of our own solar system. Billions of years from now, our sun will become a red giant, likely consuming Mercury, Venus, and probably Earth. But Jupiter, Saturn, and the outer ice giants may survive, orbiting the cooling white dwarf that was once our sun, a silent memorial to the vibrant planetary neighborhood that once was. Such a world would need a cosmic architect, a perfect alignment to defy the chaos. One of the most ingenious theoretical solutions for habitability in a binary system is known as the polar configuration. This idea reimagines the very foundation of a planet's orbit to engineer climatic stability from celestial motion. Instead of orbiting in the same flat plane as the two stars, which subjects the planet to their wild swings in combined brightness, the planet's path is tilted dramatically. Imagine a planet whose orbit stands nearly on its edge, at a 90-degree angle to the binary pair's own dance. From this polar perspective, the geometry of light changes everything. Throughout its year, this world would present different latitudes to the binary stars as it moves along its upright loop. The combined light from the two suns would sweep across the planet's surface like a slow-moving spotlight, from the North Pole down to the equator, then over to the South Pole and back again. This sweeping motion could act as a powerful climate equalizer. When the stars are huddled close together, their intense, focused heat is not trained on one hemisphere for the entire stellar orbit. Instead, that searing double sun phase shines on the polar region currently facing them, which, due to the high tilt, would naturally be colder and could better absorb the extra warmth without boiling away its oceans. Conversely, when the stars are far apart in their orbit and their light is feeble and separated, that dim phase shines on the planet's equatorial region, which is naturally warmer and might resist freezing over completely. The result is a planet that experiences a global circulation of heat, a kind of celestial averaging effect that smooths out the most violent temperature swings. Instead of a hemisphere baking for decades and then freezing for centuries, the entire planet might cycle through more moderate, Earth-like seasonal changes as the stellar spotlight migrates from pole to pole. It is a breathtakingly elegant solution, using orbital mechanics as a climate control system, turning the planet's own tilted path into a shield against the binary star's inherent instability. For life, this could mean the difference between a world of perpetual climatic catastrophe and one with stable liquid water, continents, and weather patterns that, while strange, are at least predictable. This polar configuration remains a compelling theory, a blueprint for how a world might find a precarious peace in the double light of its suns, science fiction has long been our guide to these impossible skies. For generations, storytellers have used the image of twin suns to instantly signal a world of wonder and alien grandeur. The most famous of all is, of course, Tatooine, the desert planet from Star Wars where Luke Skywalker watches a binary sunset, a moment of quiet longing that became an iconic piece of cinematic history. That single scene did more than just establish a setting. It planted the idea of circumbinary planets firmly in the public imagination, making a double sunrise feel not just possible, but poetically inevitable. Yet science fiction has also explored the darker, more chaotic potential of these systems. In Liu Cixin's monumental novel, The Three-Body Problem, an alien civilization evolves on a planet orbiting three suns in an unstable gravitational dance. Their world is subject to chaotic eras, periods of extreme and unpredictable climate swings when the planet is flung between its stars, alternating with brief, stable civilized eras. This is not just a backdrop, it is the central driver of the entire plot, shaping a civilization obsessed with predicting the unpredictable and surviving cosmic chaos. These stories, from the nostalgic beauty of Tatooine to the existential dread of Trisolaris, have done the vital work of preparation. They have trained our minds to accept the strangeness of binary systems long before our telescopes confirmed their reality. Now, with each new discovery like Kepler-16b or the triple-starred HD 131399, the line between science fiction and science fact blurs a little more. Writers and filmmakers are no longer just imagining wild scenarios. They are consulting astrophysical models. The next generation of stories will be informed by the real climatic swings, the tidal heating, and the precarious orbits we are now beginning to understand. This creates a beautiful feedback loop where discovery inspires art, and art, in turn, inspires a new wave of curiosity about what might truly be waiting for us in the light of two suns. The intricate celestial clockwork of a binary system is more than a spectacle. It is a precision instrument for probing the deepest laws of the cosmos. When you have two stars and a planet, all moving in a complex gravitational dance, every eclipse and every orbital wobble becomes a data point of exquisite accuracy. This allows astronomers to perform a remarkable kind of cosmic experiment, using the system itself as a natural laboratory to test the very fabric of reality as described by Einstein's theory of general relativity. In our own solar system, we see subtle hints of this, like the slow precession of Mercury's orbit, a tiny deviation from Newton's predictions that Einstein's equations perfectly explain. But a binary system, especially one with a planet, amplifies these effects dramatically. The gravitational pull between the two stars and the planet creates a symphony of motions, each influencing the other in measurable ways. By tracking the precise timing of stellar eclipses and planetary transits over years and decades, scientists can detect incredibly slight variations, delays of mere milliseconds in the clockwork. These delays are not errors, they are signals. According to general relativity, massive objects warp the spacetime around them, like a heavy ball resting on a stretched rubber sheet. This curvature affects the path of light and the flow of time itself. In a tight binary system, as the stars whip around each other, they drag the fabric of spacetime along with them, an effect called frame dragging. A planet orbiting through this twisted spacetime will have its path minutely altered, and light from one star, traveling to us past its companion, will be slightly bent. These tiny effects leave their fingerprint on the precise schedule of eclipses. The most extreme laboratories for this are binary systems containing pulsars. A pulsar is a rapidly spinning neutron star that emits beams of radio waves with the metronomic precision of an atomic clock. In a binary pulsar system, where this cosmic lighthouse orbits another dense star, the timing of its pulses is affected by the orbital motion and the warping of spacetime. Add a planet into that mix, and you have a three-body gravitational puzzle of staggering complexity and precision. Any deviation in the pulsar's tick-tock that cannot be explained by the simple pull of its stellar partner could be the signature of an unseen planet, but more importantly, it tests whether Einstein's equations still hold under such extreme gravity. By comparing the observed orbital decay, the slow inspiral of the stars as they lose energy to gravitational waves, with the predictions of relativity, scientists have conducted some of the most stringent tests ever. So far, Einstein has passed every one, but the search continues because if we ever find a discrepancy, a timing anomaly that defies even general relativity's predictions in one of these extreme systems, it would be a revolutionary discovery. It would mean our understanding of gravity, the force that sculpts the universe, is incomplete, pointing the way toward a new, deeper theory of physics hidden within the dance of double suns and their wandering worlds. 30 worlds with double suns may seem like a cosmic bounty, but this is a universe of profound humility. Our current catalog of confirmed circumbinary planets numbers only in the dozens, a tiny handful of pinpricks of light against the vast, dark canvas of the Milky Way. With thousands upon thousands of binary star systems in our galaxy alone, each one a potential cradle for planets, the 30 facts we have explored are not the final word. They are the first whispers from a frontier we have only just begun to map. Every new detection, from the pioneering Kepler-16b to the multi-planet family of Kepler-47, arrives with the potential to append our assumptions. The next world we find might be a temperate, Earth-sized planet in a stable polar orbit, a diamond world forged around a white dwarf, or a gas giant with a retrograde path that defies all our formation models. Each discovery is a key that unlocks a new set of questions, forcing us to revise our simulations and expand our understanding of how gravity, dust, and time conspire to build worlds in the most chaotic of nurseries. The true wonder lies not in the answers we have gathered, but in the sheer scale of the unknown that remains. For every strange and wonderful planet we have confirmed, there are thousands more waiting in the double light, each with its own story of fire, ice, and celestial balance. Our journey to understand these systems has just begun, and the next chapter promises to be even more extraordinary than the last. These worlds of double light have redefined our very idea of a home. From the chaotic gravitational nurseries that forge them to the impossible climates they endure, planets in binary systems are a testament to nature's relentless creativity. They challenge our neat categories, proving that stability can emerge from cosmic frenzy and that life, if it exists, must be a master of resilience. The journey through these 30 facts reveals a galaxy where twin suns are not the exception, but the rule, painting the cosmos with a broader, more wondrous brush than we ever dreamed. Our search is accelerating, driven by next-generation eyes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, which will peer deeper into these stellar dances than ever before. The ultimate prize remains a temperate, Earth-sized world orbiting peacefully within the habitable zone of two suns, a discovery that would forever change our place in the universe. Until then, the mystery beckons. Which of these facts left you in awe? Could life ever find a way on a world with no true night, or beneath a sky where seasons last for centuries? Share your thoughts below, and if you crave more journeys to the edges of our understanding, subscribe for further deep dives into the universe's greatest mysteries. The cosmos is stranger than fiction, and its next chapter is waiting to be told.